I was saying my talk is based on two joint work with Yilin Shang and Caterina Berprilla, one former PhD student of mine, one current PhD student of mine. And today, the aim is to extend the reduced form setting for credit insurance markets under model uncertainty. So in presence of multiple priors. And then the second step will be to include intensity, which are following an affine processes under parameter uncertainty as defined in a previous work of Fadina, Neufeld, and Schmidt. And even more ambitious, we would like to introduce in this framework under model uncertainty a longevity bond in an arbitrage-free way. So the key ingredient would be to introduce a sublinear conditional operator, now with respect to a progressively enlarged filtration in presence of probability measures which are allowed to be mutually singular to each other. In a certain sense, what we want to do is to extend the construction of Nutzer-Van Handel, who defined the sublinear conditional operator on the canonical space and with the natural filtration. So for what concerns the literature and in insurance modeling, there were already some works dealing with model uncertainty, but only under a dominated probability family. And for financial market model, of course, there is a much wider literature spanning different approaches from capacity theory, stochastic control technique. I recall the seminal paper of Dennis Martin, Sona Tuzi and Shang, and of course, all the papers on the G expectation of Peng and co-authors. A pathway approach was provided in several papers of Marcel Nutz and different co-authors. The point is that this pathway approach actually works on the canonical space, endowed with the natural filtration, as already said, and it cannot be immediately extended if you are consider different kind of filtration, for example, allowing a dependency structure. In a paper of Aksamit, Hu and Obloy, they solved the problem for initial enlargement of filtration. But now, if we are considering a credit model setting, we wish to represent an event which occurs as a surprise, like the default of a firm or the disease of a person. So our aim was to extend the reduced framework setting of Bialetti-Rokowski in presence of multiple priors. And so the key ingredient will be to define a sublinear conditional operator with respect to a progressive enlarged filtration. How can we do this? So I will recall first the approach of Nutzer-Van Handel just to get motivated. Of course, everything is very technical. I have not the time to go on all details. I will try to present this so that you can understand the reason behind it. But of course, you can find all technical details on the slides and in the papers. So let's start with omega. We can consider it as the space of càdlàg function starting from 0, or you can even consider this as a space of continuous function if it's simpler. And we assume that this omega is endowed with the Borel sigma algebra F, and P omega denotes the set of all probability measures on this measurable space omega F. On omega F, we have the canonical process B, and we denote its raw filtration by F. A particular role is played by the universally completed filtration F star, which is the filtration completed with all the P null sets for all P probability measures on this omega F. And now we select for some reason, a particular choice of this family of priors, which we denote from now on by P. And now you have already seen the talk of Shiger-Penn, so you are familiar now with G expectation. In order to define a sublinear operator, or in this case, a conditional sublinear operator, actually what you are aiming to is to pass together, to glue together the different conditional expectation under each element of this family P. And basically you have two ways of doing this. Either you assume more regularity on the random variables, as in the case of the G expectation, or you assume some conditions on this family P that you can find in the paper of Nutz and Van Handel. And these properties that must be satisfied by the elements of P are properties of measurability, invariance, and stability under Pastin, which I have not the time to comment. So what is the key ingredient to construct this F conditional Subline operator is to work with the so-called concatenation of two paths, omega and omega prime at the stopping time tau, which is the path that you obtain by following omega up to tau and then afterwards to following omega prime. Given a function x on omega, then we can define the function x tau omega, which is the function evaluated on the concatenation with omega at tau. Why is this function fundamental? Because now, under the assumption that our family of priors satisfies this hypothesis of measurability, invariance, and stability under Pastin, we can define a function epsilon tau for every function x, which is assumed to be upper semi-analytic. That means that the sets x greater than c for all c in R are analytic. That means there are functions that are imaged through a Borel function of Borel sets coming from a Polish space. Very complicated. There is a reason for this, but let's keep it. So now what is this operator epsilon x is given by the upper expectation, by the capacity associated to these elements in the family of priors P. So it's the sup of all P in this family P of the expectation under P on X evaluated on the concatenation with omega at tau. This operator is F star tau measurable, upper semi-analytic, and it does the job. That means that it coincides with the Pastin, with the up tau conditional expectation associated to the element P prime in this family P. Or precisely, this epsilon tau x is equal to the central sup over all P prime, which coincides with P on F tau of the conditional expectation under P prime of x given F tau. And this holds P are more surely for P in this measure. In particular, a consequence of this pathwise construction is that the tau property is satisfied by this operator. So if sigma is another stopping time, less or equal than tau, then you have that epsilon sigma applied to x is actually equal to epsilon sigma applied to epsilon tau, as in the case of the standard conditional expectation. Okay, so let's move on and try to construct this Subline conditional operator for a progressively enlarged filtration. The first step is to identify, to start with a given gamma process, which is assumed to be equal to the integral of a certain intensity mu. And now we follow the standard construction for totally inaccessible stopping times, so the Cox construction. And we consider an additional probability space, omega hat endowed with the Borel sigma algebra and probability measure p hat, and a uniformly distributed random variable C. In particular, this probability space is supposed to be atomless. And now we define tau tilde as the first time where gamma t, the hazard process, is greater or equal than minus the logarithm of this C, this uniformly distributed random variable. So in particular, we are defined tau tilde as a random variable on the product space omega times omega hat. On this product space, we consider the filtration G generated by the filtration F of the canonical process and the filtration with respect to which the jump process associated to tau tilde is measurable. Then we consider now on this product space omega tilde in the family of probability measure, which is generated by considering the product of the elements P in this initially selected family of priors P with P hat. And now the construction of our G conditional Sublinear operator is based on this result that any, let's say, sufficient integrable random variable x tilde on this product space can be represented as a function phi, a measurable function phi of tau tilde and omega. And now I need to introduce quickly some, some notation. One, we denote by the epsilon tilde the capacity of the upper expectation associated to the family P tilde. Then G P or G calligraphic P will be the sigma algebra or the filtration completed with the null set for a family of priors P or for the single probability P. And L1 omega tilde will denote the measurable function with finite capacity. And finally, by the expectation of the P hat of x tilde, we will mean the integral with respect to the second variable, omega hat. Okay, so we are now ready to introduce this definition. So suppose now that our family of priors P on omega f satisfy the assumption of measurability, invariance, and stability under pasting. And consider an upper semianalytic function x tilde, which has finite capacity, or at least is non-negative. Then define the following function, epsilon tilde t of x tilde, which is equal on the set where tau tilde is less than or equal than t to epsilon t of phi applied to x, and then x is evaluated on tau tilde. And on the set where tau tilde is strictly greater than t, this coincides with epsilon t applied to a to the gamma t times the expectation under P hat of x tilde up to time tau tilde. Here recall that epsilon t is the F conditional Sublinear operator. This function epsilon tilde t is well defined. I recall, sorry, that this phi is the measurable function which characterizes x tilde as a function of tau tilde and omega. In particular, this epsilon tilde, this operator, is the operator that we were looking for because it does the job in the sense that it coincides with the upper conditional expectation with respect to this family of priors P tilde, which is selected, and the filtration GT. So more precisely, epsilon tilde t of x tilde coincides with the essential sup over the P tilde prime, which coincides with the P tilde on GT of the conditional expectation of x tilde under P tilde and GT, P tilde most surely for all elements in this family. What are the properties of this operator? Of course, this operator is sublinear in x tilde, is measurable with respect to the universally completed filtration, it maps upper semianalytic function into upper semianalytic function, but I have a bad news. That is that the Tower property does not hold in general, but we can prove only that in general we have a weaker Tower property. That means if you now consider S less than T, then epsilon tilde S applied to epsilon tilde T is greater than or equal than epsilon tilde S. And why it is like this? So if you pay attention, now we are requiring here, in order to compute epsilon tilde t, that x tilde is integrable, or at least non-negative. And we didn't have this kind of integrability conditions by the definition of the F conditional Sublinear operator. And the fundamental thing is that for the F conditional Sublinear operator on the canonical space, you can have this pathwise construction. But this cannot be done on this product space and with this progressively larger filtration. So in order to define this operator, you need to apply Fubini-Tonelli. So you need to exchange the order of this integration. And especially to prove the Tower property, then you have places where in the proof you have to exchange expectation and essential sup. In particular, this operator does not map L1 into L1, so you will lose integrability and sometimes measurability. However, there are sufficient conditions, for example, the commutability lemma of Yan, which guarantees when you can exchange the order of integration between expectation and essential soup, or there are other sufficient conditions that can be found. In particular, there is a good news, because if you are interested in modeling of insurance market or credit risk markets under model uncertainty, then you will usually consider specific kind of products. For example, like a product which guarantees a payment Y if there is no default up to time of maturity, or it guarantees a recovery payment set at tilde tau at time tilde tau if this default has happened before or at capital T, time of maturity. For this kind of product, if the process set and the random variable Y satisfy some integrability and measurability condition, then we have that the G conditional operator actually maps L1 into L1 and the tower property holds. In particular, one can prove that if under certain technical conditions on the set of P, and then also transfer to P tilde saturation, and you assume, for example, that this under these priors, the underlying price process are sigma martingale, then we can also interpret this epsilon tilde as a superedging price. So in particular, let's have a look at this formula on the bottom of the slides, where you see that if you have an annuity, then epsilon tilde t of this annuity actually coincides with the up to time tau tilde with F conditional operator of Y times E2 minus the inter between small t and capital T of mu in the U. And so the question is now, can we compute these sublinear expectations, conditional expectation, as in the case, for example, of affine processes under one prior? And the second is, can we now use this general framework in order to introduce the notion of a longevity bond under model uncertainties in an arbitrage-free way? And these are the questions that I'm trying to answer in the second part. To do this, very shortly the definition of fine processes under parameter uncertainty as given by Fadina, Neufeld, and Schmidt. So now we are interested in priors under which our canonical process is a PF semi-martingale with absolutely continuous characteristics associated with the predictable process beta P and alpha. And we fix compass set theta, which is a product of intervals, and consider the set value functions B star x and S star x. For each x, this corresponds to an interval. And now we say that having fixed this theta, we say that a semi-martingale law P is affine dominated on the interval small t capital T by theta if the semi-martingale characteristics of the canonical process are such that beta PS belongs to beta star BS and alpha S belongs to A star of BS, that P, that T almost surely. And what does it mean? It simply means that the semi-martingale characteristics of the canonical process are bounded by affine functions of the canonical process. So now it's time to introduce our market model. So now we consider a canonical process with two dimensions. The first dimension BS will be used to model a risky asset. And the second component will then represent, for example, mortality intensity on this market. In particular, for the sake of simplicity, we assume that we have a risk-free asset which is equal to 1. And now we wish to define on this, we wish to consider on this probability space a family of priors with the intention that we have a particular structure for the mortality intensity and a particular structure for our asset prices. How can we do this? We say that a probability measure belongs to the set A mu T theta if under this P mu is a semi-martingale law for the second component of our canonical process, and P mu is affine and dominated on the interval T, capital T by theta, where theta is this fixed product of intervals. And then we consider now for each T on omega in 0T times omega x, a family of probability measures, which is given by all elements in this initially selected family P, which also belongs to this set A mu of semi-martingale measures, affine dominated by theta for B mu. In particular, we also assume that P, of course, satisfy these assumptions of measurability, stability, and invariance, but also that under each of these priors P, the process S is a PF local martingale. In this way, by this definition of these families of probability measure, zeta T omega, we obtain two things. The first one is that under these probabilities, our intensity will have a structure of a affine process with under model uncertainty in a way that I'm going to show you in 1 minute. And under each P, under each model P, the resulting market is arbitrage-free. In particular, we show that for each T on omega, set T omega satisfies this assumption A, that means that these priors are satisfy this hypothesis of measurability, invariance, and stability under pasting. So that means I can use this family first to construct the F conditional operator and then the G conditional operator, and still preserve this characteristic of the market. Why is this important? Because I come back to the first question that I posed, that was if we can compute this F conditional Sublinear operator as we would be in a standard affine setting. So consider now this result, which extends a result of Fadina, Neufeld, and Schmidt. So for simplicity, assume that now the second component of the canonical process is always non-negative, P that T almost surely for P in this on the initial family of priors, and then suppose that there exists a P bar in Z and a P bar F Brownian motion W, such that the canonical process under this P at satisfy this CM model. Then actually, we can show that this P bar is maximal in the sense that the F conditional Sublinear operator epsilon T applied to e to the minus the inter between T and capital T of the integral of the intensity is equal to the exponential of phi plus psi times the canonical process times small t, where phi and psi are these deterministic functions solving these Riccati equations. The key is that to show that this P bar is maximal, that means that epsilon T, which is this essential soup of this conditional expectation, actually reaches its maximum, and the maximum is evaluated in P bar almost surely. So by assuming this affine structure, under parameter uncertainty for mu, we can provide analytical results where we can compute these Subline operators. And now let's move forward and try to answer the second question, that was, can we extend this setting further and, for example, use it to introduce the notion of longevity bond in a way which is arbitrage-free. So now, what is how is defined the longevity bond in the standard literature? Usually, we follow the definition given in Cairns, Blake, and Dow, and define a longevity bond with a certain maturity T as a bond which pays the so-called survival index at time capital T. And this survival index is defined as the exponential of minus the integral between 0 and capital T of the integral of the intensity. So now if we consider a standard model with one prior, we can suppose to have a certain martingale measure coming from the financial market model. Then we can use this martingale measure to price this longevity bond. But this is, of course, not the case in our setting where we are considering a family of possible probability models. So how can we introduce a price process for this longevity bond and extend the market in a way that the resulting market model is arbitrage-free? And first of all, what does it mean that the market model is arbitrage-free under model uncertainty? In order to do this extension, to provide this definition, let's consider our candidate price process, which is given by Sy of T, the G sublinear conditional operator epsilon tilde applied to the survival index at time capital T. In particular, you can intuitively think that this could be a good definition in the sense that is the upper price that you can have by looking at all these different models. As a technical reason, we will assume from now on that this epsilon tilde is càdlàg path. But if you interpret this as the upper possible price, you can even skip it. This is necessary if you want to use the fact that this epsilon tilde as an interpretation under some condition in the family of priors as superedging price. But as I said, I have no time to do this now. And now we will consider how to introduce this definition of arbitrage-free market model. In particular, before I do this, let me remark that in the paper we prove different sufficient condition which guarantees that this operator has càdlàg paths. For example, this is the case if you consider the extension of this operator coming from the G expectation on the random G expectation. And now I recall the concept of absence of arbitrage of the first kind as introduced under model uncertainty as introduced in a paper of Sarah Biagini, Bouchard, Cardaras, and Marcel Nutz. In particular, we focus on trading strategies, which are assumed to be simple. That means constant over random intervals. And for the sequel, we denote by L0 plus the random variables which are zeta tilde quasi surely finite. And now we, to a given simple predictable strategy, we associated a wealth process x of xh, which starts from h and then results from the investing through this simple strategy. In particular, H simple denotes the family of of strategies such that guarantee that our wealth process is bounded from below, let's say, non-negative. And now consider the definition of superedging price for a given claim F. in L0 plus, which is defined as the smallest initial capital that such that there exists a simple strategy whose terminal well process dominates f zeta tilde quasi surely. Then we say that the market model 0S extended with this price process for the longevity bond presents no arbitrage of the first kind with respect to zeta tilde if when we have that for every S in 0 capital T and contingent claim F, the superedging price of F is 0, this implies that the contingent claim itself was 0, zeta tilde quasi surely. Okay, and now consider a claim Y, or consider the Y as the terminal value of this survival index, and suppose that Y is an upper semi-analytic sufficiently measure a non-negative random variable such that epsilon tilde T applied to Y is càdlàg. Then if for every well processes associated to a simple strategy in satisfying this non-negativity condition, if for all these kind of well processes we have that for all T in 0T, the expectation de P tilde of the well process at time T is less or equal than the expectation de P tilde of the well process at time 0 for each P tilde and zeta tilde, then the extended market model satisfies no arbitrage condition of first kind. That means that if this condition holds for every T and under each element of this family of priors, then we have introduced a price process for our longevity bond in an arbitrage-free way. So you will maybe wonder on this condition. This condition is actually the price that, let's say, so we have to pay in order to take in account model uncertainty. But this is not actually very difficult to realize condition. For example, let's have a look at this list. If you have that there are a lot of different sufficient conditions that guarantees that this condition holds. For example, suppose that your well processes are P tilde super Martinger for all P tilde in this family of priors. Then this also implies that our condition holds. And this is simply means that under each element P tilde that you have chosen, the underlying market model is arbitrage-free. Or, for example, another condition is that if you have that the asset price always non-negative, zeta tilde quasi surely, and in the case we do not allow short selling in the asset price as well in the longevity bond, then again we have that this condition of this proposition holds. Of course, this may be restrictive for financial market, but this is a usual restriction for insurance companies. And so here I would like to stop and thank you very much for your attention.
Thanks a lot, Francesca, for a very nice, although technical talk, I must say. So, let's see if we have any questions in meantime. As always, you can either raise your hand or post them in the chat or in the Q&A, whatever works for you, the audience. And by that time, maybe I'll have a quick question, actually, maybe not very fair question, but so if I'll take, did you try actually to take any market data and see how this works? And the question is, if you take that market data, can you somehow infer how much of model uncertainty is shown into what you observe? For example, at the bid-ask spread, of course, here it is bid-ask spread of whatever contracts you are taking, or bid-ask spread of the credit spread.
So this is a very interesting question. I do not have an immediate answer for this. There is a paper of Filipovic and Cambou, who is actually proposing like a fitment mechanism to, let's say, to calibrate on some probability and then make a check again your model and recalibrate this. But this question, I cannot answer this question from this setting. Yeah, but it would be, of course, very interesting to be considered, how to realize this, starting from these definitions.
Right. So what would be the range of those parameters that actually match the, I don't know, maybe with a spread, maybe something else.
But for example, in the talk of Shige Peng, there is already a lot of hints how to do this, because he was proposing what are the best estimators, for example, for this range mu bar, mu up, upper mu.
Right. So yeah, that of course the natural next question exactly to do the inference actually of the parameters based on, I don't know, in your case, nonlinear G expectation and match the parameters and using that. But yeah, that would be interesting actually to look at that. So yeah.
But as I said, I mean, if you consider the G expectation, Shige has already done a lot in this direction. This is, I mean, this is a really very general setting. You don't even know what is this family of priors P. On the contrary, at least in concrete models like the G expectation or the random G expectation, you know that this G expectation is associated to the capacity of the laws of integrals of respect to the Wiener process, where sigma simply, the limitation that you have on sigma is that there's a limit in between some bounds or some random bounds.